The root mean square, or RMS, is a crucial concept in electrical engineering. It represents the value of a direct current that would produce the same heating effect as the alternating current. Today, we will derive this value specifically for a triangular waveform. Triangular waves are frequently encountered in power electronics and signal processing. Understanding their RMS value is essential for calculating power dissipation and designing efficient circuits that handle non-sinusoidal periodic signals without overheating components. To begin our derivation, we define the mathematical function of our wave. For a symmetric triangular wave with peak current im and period t, the current rises linearly from 0 to its maximum value over the first quarter of the cycle. The RMS value is calculated in 3 steps. First, we square the function. Second, we find the mean or average over one full period. And third, we take the square root of that average. This mathematical sequence gives the formula its name. Because the triangular wave is symmetric, we can simplify our integration. Calculating the average of the squared function over just the first quarter cycle and multiplying by the appropriate factor yields the same result as integrating over the entire period. In the first quarter cycle, the current is a straight line passing through the origin. The slope is the peak value im divided by the time t4. This gives us the simple linear expression I, t, equals 4 times im divided by t, times t. Next, we square this expression as required by the RMS formula. Squaring the constants and the variable t gives us 16 times the peak current squared, divided by the period squared, all multiplied by t squared. Now we substitute our squared function into the mean value integral. We can move the constant terms outside the integral sign to simplify the calculus, leaving us to integrate only the t squared term with respect to time. Using the power rule for integration, the integral of t squared is t cubed divided by 3. When we evaluate this from 0 to t over 4, we get t cubed divided by 64, all divided by 3, which simplifies to t cubed over 192. The final step in the root mean square process is to take the square root of our mean square value. The square root of im squared over 3 gives us the final elegant result, the peak current divided by the square root of 3. Let's apply this to a real scenario. If you have a triangular current with a peak value of 10 amperes, its effective or RMS value is 10 divided by 1.732, which equals approximately 5.77 amperes. To find the power dissipated by this triangular wave through a 10 ohm resistor, we use the RMS value. Squaring 5.77 and multiplying by 10 ohms gives us a power dissipation of 333.3 watts. It is helpful to compare this to a standard sine wave. While a sine wave's RMS is peak divided by the square root of 2, a triangular wave's RMS is peak divided by the square root of 3, reflecting its lower average energy content. Remember these key points: the RMS value represents the effective DC equivalent for heating. For any symmetric triangular or sawtooth wave, the factor is always 1 over the square root of 3, regardless of the frequency or period of the signal. Test your understanding. If a triangular wave has a peak-to-peak value of 20 volts, what is its RMS voltage? Remember that the peak value im is only half of the peak-to-peak distance. Calculate it now before the answer appears. You have successfully derived the RMS value for a triangular waveform using calculus and symmetry. This fundamental tool will help you in all your future circuit analysis and power calculations. Generated by Vision Solve AI.